Welcome everyone, my name is Mathias Delahaye and I'm going to present you our work on the importance of providing a tangible haptic response for training CPR in VR. This study was performed in collaboration between the Immersive Interaction Group from the EPFL and the company B-Rescuer providing first aid trainings. The idea was to explore CPR training in an embodied virtual reality simulation. So let's briefly introduce the notion of embodiment. According to Kilteny et al., the sense of embodiment is composed of the sense of body ownership, the fact that I own the virtual body, the sense of agency, the fact that the virtual body moves as I do, and the self-location, I am located where the virtual body is located. Also, studies showed that human intelligence relies on the embodiment in the sense that a body is required for intelligence. So the first question we may ask is why this study matters. So we observed that many people were afraid to perform CPR due to the emotional stress of the situation. Indeed, someone is about to die if no one does anything. And at the same time, that traditional CPR training doesn't induce such emotional stress. Indeed, you are in a room with a trainer and a mannequin and nothing can really happen. So the idea of this experiment was to rely on the embodiment to infer the emotional stress of the situation, to prepare participants for such emergency, and thus to increase the quality of the training. Our first investigation showed that CPR in VR is a widely studied research area, that many VR applications doesn't use a mannequin to train CPR, or on the other side use very complex setups or expensive ones, and finally that study in most of the time doesn't assess the quality of the data from the tracker. So few studies were assessing the quality of CPR training using a mannequin and consumer-grade devices. Our choice was to use consumer-grade setup. Thus, we only use HTC Trackers, providing a single hand tracking, rigid one, so without any finger motion or without the integration of the full body in the simulation. And we choose to use a professional mannequin to provide realistic haptic feedbacks. This study aimed to show the impact of haptic feedback and live displayed CPR performances. Thus, we didn't put the emphasis on the scenario or on advanced graphics for this context. This leads us to the two research questions. Is the combination of VR with a mannequin capable of increasing CPR performances? And how can we assess the tracker reliability? To answer the first question, we set up the following experiment, where a participant has to perform CPR on the mannequin, as we can see on the video. And on the virtual simulation, we have the same environment with two gauges representing the frequency and the amplitude of the movement. There is also a graph showing in real-time depth compressions. As we can now see, the HMD allows to have a first-person point of view to have an immersive setup. So we formulated the following hypothesis. The first one, that we expected a normalized presence score to be higher than 0.5, as hinted from the literature. The presence score was measured using questionnaires. We also used questionnaire to measure agency score, and we formulated our second hypothesis, placing the normalized agency score to be higher than 0.5 in all conditions. Our third hypothesis stipulated that the use of a mannequin leads to better performance than without the presence of a mannequin. The fourth one, that adding real-time performance indicators would lead to better performance than without. And the fifth one, that displaying in real-time live performance would reduce the level of presence. To answer this hypothesis, we used the following protocol, where each participant were trained during 10 minutes basics for CPR massage. So we taught them the right frequency and the right amplitude for a correct CPR massage. So for the amplitude 6 centimeters and for the frequency around 120 compression per minute. Then they would have to establish some baselines. So they would have to perform during 2 minutes CPR session. So first with the mannequin and second without the mannequin. During the baseline, as we can see on the right side, there were no HMD, thus no live display performances. And then after, participants would have to perform the same session, but alternating between the condition A1, A2, B1, B2 in a counterbalanced order. And after each session, they would have to fill a questionnaire, which also served as a rest time. At the end of the experiment, participants were invited to give their feedback on this experiment. This experiment was performed on 12 healthy participants, including 4 females. All participants were right-handed but had the ability to choose for left-hand representation. And finally, the time range for the experiment was between 16 and 56 years old, with a median average year, with a median year of 27.5 years. The analysis showed us that the samples from the live performances were not normally distributed, as we can see on this table. And as data from questionnaire are drawn from discrete value, we were not able to use parametric tests, thus we only use non-parametric tests followed by correction. So in our case, Wilcoxon-Wrongsum test and Bonferronis correction. Results for present score are plotted on the left plot, and as we can see, except for realism, present score were all above 0.5. Thus, we partially accepted our first hypothesis. For the normalized agency score, we can see on the right plot that all scores are above 0.5, thus validating our second hypothesis. For the 5 hypotheses, we can see between the difference between A1 and A2, or between B1 and B2, that live display performance didn't significantly reduce the level of presence. Thus, we rejected our 5 hypotheses. Concerning CPR performances, we can see on the left side of the left plot that even guided, in the non-mannequin condition, subjects struggled to reach the expected amplitude of 6 centimeters, whereas they did manage to reach this amplitude with the presence of the mannequin. So without the mannequin, it's the A0, A1, and E2 conditions, and with the mannequin, B0, B1, and B2. Thus, this allows us to validate our third hypothesis, but as we didn't observe any difference between A1 and A2 or B1 and B2 conditions, we didn't highlight a significant added value of live display performances. Thus, we rejected our fourth hypothesis. So to sum up for the hypothesis, we partially accepted our first hypothesis, placing the present score higher than 0.5 in all conditions, with the regard of realism, in which case this was not observed. For the second hypothesis, we also we validated this one, as we also observed a normalized agency score to be higher than 0.5. Our third hypothesis was validated, as without the mannequin, subjects struggled to reach the right amplitude, but did manage to reach the right amplitude with the presence of the mannequin. Our fourth and fifth hypotheses were both rejected. The fourth one because we didn't observe any added value from the live display performances, and the fifth one because placing live display performances didn't hamper the level of presence. So while we performed this study, we also took advantage of our setup to assess the fidelity of the tracker. This study used a Brayden professional mannequin, which integrated an internal probe. We connected this internal probe to a computer thanks to a microcontroller we programmed to interface as an interface. And our setup only used 2 HTC Trackers plus 1 HTC Vive, as we can see on the right side. Thus, we were able to simultaneously record data from trackers and from the internal probe. So to be able to use the internal probe as a ground truth reference, we had to calibrate it, as we can see on the left plot, on the left side, and we established our calibration curve on the right side that we implemented on the microcontroller. Thus, we were able to consider the data from this sensor as a ground truth reference for a comparison. So these are some subsamples from data we recorded. So as we can see, there is a vertical offset between the data from the trackers and the data from the internal probe. It's more difficult to see, but there is also a temporal offset, and we can clearly observe that there is a huge difference in the refresh rate from both input methods. Thus, we had to pre-process in the first time this data to compare both inputs. The first step of the pre-processing was to realign both samples. So as we can see on the right side, the red curve represents the data from the internal probe, so our ground truth, and in the blue we have the data from the trackers. So the first step was to remove the temporal offset to obtain the orange curve. This was performed by extracting a 5-second subsample of the data from each trial, and to introduce a short temporal offset, and each time computing the cross correlation between the ground truth reference and the offsetted sample, and to retain only the offset providing the highest cross correlation. Once we temporally realign both samples, so we obtain the orange curve, we did the same process to remove the vertical offset and obtain the green curve. Once both samples were realigned, so temporally and vertically, we undersampled the data from the internal probe to match the refresh rate of the trackers. We also capped the value to positive compression depth, as the internal probe cannot measure the height of the hand if the hand is higher than the surface mannequin. And finally, we slice all samples in compressions. From this analysis, we observed that we had depth spikes when the compression is at its maximum. This might be explained by the fact that the tracker is attached to a strap, and with its inertia, the tracker may move while we perform CPR massage. And the second observation is that a drift occurs within each trial. So if we compare the data from the tracker at the beginning of the trial and at the end of the same trial, the data are offsetted by 1 centimeter, roughly 1 centimeter, at the end of this trial. This goes towards the direction of the mannequin. So this gives us the following result. So we can use the trackers to correctly measure the CPR frequency, as this was already shown in the literature. But we also observed that the data from the tracker present a difference in the measured amplitude during dynamic movement. Thus, we need to pay attention and to scale the data from the trackers if you want to recover the right amplitude for the movement performed. In our case, we observe a factor of 1.33 between the tracker amplitude and the internal probe amplitude. So the take-home message of this study is that tracking a single hand is enough to provide an accurate frequency feedback and to secure a minimal embodiment level, even though we only have like a rigid hand without the presence of the full body. That using raw tracker data may lead to depth measurement discrepancy, which may lead to biased CPR amplitude training. And finally, that real mannequin remains compulsory to correctly train CPR amplitude. So thank you very much for your attention. Do you have any questions?